if we consider antisymmetric, the system is antisymmetric, like the fermions. Okay, I can read for you. Yes, I told them for the midterm, if you, I can postpone to Wednesday if you want to turn.
Thank you.
Thank you. And homework, if you can finish homework 3, right? Okay.
Thank you so much.
Still have more job, right? I think to know how to do it is more important than
I agree. It's a very long.
Yeah. That sometimes take a home is good, but sometimes not.
I thought I was the only one.
Okay, so antisymmetric definitely have a product. One is symmetric in the spatial function and spin to be antisymmetric. So that add and even multiply. So that here if we select antisymmetric in the spatial function, then the spins to be symmetric, right? Or in the spatial is symmetric, then the spins will be antisymmetric. So that is method 1. That means we construct this total wave function as the product of a total wave function for only special case and multiply the total wave function of spin. So this is the first one, and then we are going to take it. You will see the advantage of this one and the advantage of the second one. Okay, so here I just remind you how to construct those symmetric, antisymmetric for each one. For each one here, I just remind you, if we only consider special total wave function symmetric, that is n1 factorial to n factorial and capital N factorial. If you remember what is low, the n1, n2 is the factorial. We've discussed already now. I'm going to take one example and go to the detail how to determine those. So, permutation operator and apply to all each individual single particle, right? Single particle psi 1, R1. Okay, psi n. Nth particle go to the n capital N states. That is for the symmetric. For the antisymmetric, with a special total wave function, we just know that is nothing but this Slater or determinant. Right? It stays here. Okay, so psi n1 r1, psi n1 rn, and go to psi n r1, psi n rn. Then you can see here this the row. The row is states index. You see, from n1, first row is n1, second n2, and so we have how many states? And then the column here, the column is position. That is how to construct this. And for the spin, that is the space, right? For spin, special function, spin similar, but for spin antisymmetric, we need to be careful. So now let's consider spin. That is for special part. Now for spin part. Okay, symmetric, similar, like this, right? Symmetric. Here we have n1 factorial and n factorial and n factorial for all the permutation. Here the spin states m s1, s1, m sn, sn. Okay. But for the antisymmetric, let me write the same thing like this later determinant, and then we will discuss the condition in which we can apply this. There is a condition here, because that is a property of the determinant. N S1, S1, kata N S1, Sn. Okay, which was. That's fine. I mean, just index for the S spin. S, N, S, N, S1, N, S, N, S, N. So here, this is this B, in principle, let me write down here, n by n squared matrix, right? Because the determinant. But you can see here, if this is states, so how many states here? For given S, since we consider this identical particles, so if the spin same like spin half, they all are spin half. So the ms is 2s plus 1, right? So that is a 2s plus 1 state. Then here, the total number here is the number of spin. So here, then, so this be equal to the 2s plus 1. If not, then we cannot use, because, for example, we have 10 or just 3, let's say. 3 spins, but if spin is half, so we have only 2 plus minus. So you have only 2 rows, but you have 3 columns. That is not square matrix, right? So then that time we cannot. So this is only if this is a condition here, right? If number of spins equal to the 2s plus 1, then okay, we cannot. If not, okay, we can, there are 2 ways. Apply the addition in chapter 7, addition of spins that like a CT coefficient. So that is one case. Another is apply the method 2, which we are going to discuss. The second method. So that's why I first introduced this one, and you will see in most cases we have to go to this one, since there's a restriction of this later determinant for the antisymmetry. Okay. So now let's so now let's do an example. See how can we apply. Let's do a practice. Example 1. The first one is we just consider 2 non-interacting and identical particles. We are in one dimension infinite square wave. Infinite square wave. Okay, that is the picture now. Ask us first, well, that's A. Find the ground and first excited state of distinguishable particles. Okay, let's ignore spin. First case. if we consider these two particles distinguishable, how to construct the wave function, right? How to get this total wave function for the ground state and excited states. This is an end, right? So we have either ground and both ground and excited. Second one, B, found of, okay, that's bosons. That's a boson means indistinguishable, right? Space of bosons. Also, you could not be the second one. C, Hermes. You can not spin. And D, again, Hermes with spin. Okay, so there are several cases. Let's consider each case how to construct the total wave function of these two non-interacting identical particles. Okay, let's first consider the first information. Two non-interacting identical particle here. So first Hamiltonian, right? Hamiltonian, since it is non-interacting, so we can write down the summation of each individual, right? That is the first. Okay, and then we know each individual, Hi, each individual single particle in chapter 4, we already learned that is for the one dimension, right? This is the kinetic energy part and plus potential. Plus V by X, I, and the Vi, if you remember, we already discussed this. And also the return also something like that, right? Xi within the wheel, and outside the wheel, Xi, otherwise. Otherwise is ball, right? Remember this. Okay, so the solution for this, now the solution for each single, just go to details, energy, right? For single particle energy E and I, the ith particle, that in that quantum number is here, h bar square pi square n I square over 2m. Since the identical particle, right? So m, I remove the index, a square, and n I from 1, 2, 3, all the integer number. Then the single particle, the wave function, or eigenstates correspond to each individual eigenvalue. We also have this solution is 2 over a. Sine n I pi x I over a. Right, so those are the information. And then now, so the total energy, because we are going to discuss which one is ground state, which one is excited state, so we need first also know the formula for the total energy of two non-interacting identical particles is simply as a summation of each individual, right? That is total energy. Then this wave function, okay. Now I'm going to write down here. So now we are going to answer A, B, C, one by one. Now we go to A. A. So what does mean distinguish that? We can distinguish item 1 and 2. So when you interchange, it will not follow the symmetry, right? So there's no any requirement about the symmetric and asymmetry. Therefore, for distinguishable particle, the total wave function n1, x1, total wave function to be just simply the product, right? Remember we have this, since this non-interacting, Then the total wave function just wave function just simply the product of each individual. I from 1 to 2 and I, xi. And in this case, we have each individual here. So we have just simply, since a square root of a over 2 twice, so that is a removed square root, and sine n1 pi x1 a sine n2 That's all. Since then you can see when you interchange it is different. Since x1, x2 they follow different positions, you change the numbers, they're different, right? So that is how to construct distinguishable since there's no require about the symmetric. Does not hold the symmetric under this interchange. Then once we have this, we have energy. Okay, so here. That is fine. Okay, so now let's first ground state. This is general, right? Okay, if I use index n1, n2, like this. So ground state. What does mean ground state? The energy is lower, right? So now we can see here the energy is lower since ni from 1 to the lowest speed ni equal to 1. So both are 1, right? So then that is E1 equal to E1 plus E1, right? And that is the number if you want. So that is I squared over m a squared, right? Because this factor 2 is just add good. Okay. That is the ground states, energy and ground states V11. Sine 1, x1, sine 1, x2, right? That means n1 equal to n2 equal to 1. That's the ground state for this case. And you just see here, if this is 1, so that is 2 over a sine pi x1 over a sine pi x2 over a. The configuration is here, right? So that is n. Ni equal to 1, so we have two particles here. If Ni equal to 2 is steady state, right? So that is picture. How this two particle occupy the energy level is a single energy level, right? Epsilon I. Oh, okay. If I use capital, so then capital. All right. Each single particle. Then we have two particles, also distinguishable, so we can give an index. And but they are all in the same. So that is this one. Any question? Not now. First, excited state. First, excited states should be one of them go to the second one, right? So that is to go to highest. Okay, so that means n1 equal to 1, n2 equal to 2. Or, since it's distinguishable, so n1 equal to 2, n2 equal to 1, right? There are two cases. So the configuration in this case, right? Okay, that's the ground state. So, here, that's be 1 here, 1 here. So this is a 1, 2, 1, 2, right? So that is a ground. This is the first excited. Right, like this. Okay, so since we know this, so then let's look at energy. Energy first excited is equal to E1 plus E2, right? And E1, E2, whatever is N1 equal to 1, then N2 equal to 2, or N1 equal to 2, N2, the number 6. So that is 5 h bar square. So you can see the degeneracy, right? For m a square. squared. That is its energy for both. Then this is excited states, right? Energy, right? So excited states, there are two cases, right? Either is 1, the first particle is 1, x1, side 2, x2, or side 2, x1, side 1, x2, right? There are 2. And you will see the state is not the same, so then you'll see this. Okay, for example, here is over 2, 2 over a sine, if n1 x1, so the pi x1 over a, sine 2 pi x2 over a. Another is 2 over a, sine 2 pi x1 over a, sine pi x2 over a. Yes, they are not same, right? So what's the degeneracy? It's 2, right? Okay. So this is for distinguishable. Now let's go to the next one. 2 bosons. Let's see how to determine the total wave function 2 bosons and what is the ground state energy and states and excited states energy and states, right? So now let's go to B. Bosons. Bosons immediate means that is indistinguishable and speed hypersymmetric, right? So not anything. So for bosons, okay, energy, again, n1, n2 is simply still n1 plus En1 plus En2. This is no change. The particle energies, but the wave function should be symmetric, right? That is implied, like the winter exam, you know that. Okay, so we ignore spin, right? If you ignore spin, so I just use the position x and x1, x2, and by I erase. By definition, it must be n1 factorial, n2 factorial, and n factorial, right? And sum of all the possible permutation. Now here is only 1, 2, right? Because there's only 2 particles, n1, x1, n2, x2, right? Okay. So that is the general. Now we are going to discuss like this. We got the general formula. Now we are going to, what is the ground state? Ground state means its energy is lowest. So in this case, the lowest energy is n1 equal to n2, 1, right? Because no restriction. So n1 and 2 equal to 1. And then we have this ground is equal to E11, right? Or, yeah, and that is the symmetry method. So that is H squared over MA squared. Okay. Ground states. If you want to make this thing, I use another index here. So that is the symmetric ground state. Here, this we already discussed which n1, n2. So here n1, n2 is given. Okay, so now, we need, let me first write down here n1 factorial, n2 factorial. So n is 2, right? Total particle is 2. Now here, P12, say 1, right? Because n1 equal to 1 to say 1, x1, say 1, x2. Now, how to determine the n1? How much? The number of particles in this state, right? How many particles in the n1? 2, right? Okay, so here, 2 factorial. Any particle in n1, no, right? That's 0, yes. That is how to determine. You just look this one, right? How many particles in the state 1, how many particles in state? So now, and this is 1, right? And here, the permutation here is for all these different states permute. But here, n1, those same, right? So there's no permute. So that is just simply product. Okay, and then you can, since this factorial, so that is very simple, similar like this, right? Sine inverse y, right? Pi x1 over a, sine pi x4 over a. That is the ground state. Okay, and the occupation here is two particles, n I equal to 1, n I equal to 2. So only here, right? No distinguish. Here I can distinguish particle 1, particle 2, but this indistinguishable. Only know there are two particles stay at the ground state. The matter equal to 1 state. That is ground state. That is ground state. Energy, that's ground state function. So here we go to the details. You know how to determine those, right? Remember, and how to permute this permutation. Okay, and space. No. First, excited states. First, excited state. So n1 equal to 1, n2 is equal to 2, right? Or n1 equal to 2, n2 equal to 1. The occupation here, one is here, another is here. But we do not know, not like this. This distinguishable, so we have two states. Here, indistinguishable, so we have only one state. Right? But let's play, you will see. So now energy excited, use the index of first, right? So that's be E12, okay. That is E1, okay. Here, let's be here, yeah. When I say 2 here, it's index of, index is not particle index, it's the Ni, right? So, if I say that the Ni, then it's the same thing. Plus square, plus over 2 and a square. Now, so now, the first excited states symmetry, so you have a symmetry. And first excited states. So again, we're going to write down this general formula. Then we are going to substitute this each individual. Well, this is 1, 2, n1, x1. Yeah, this is a general formula. Then we are going to see here. This is in case n1 equal to 1, n2 equal to 2. So how many n1? Capital N1, only 1, right? Yes. 1 factorial and 2 is only 1, right? So 1 factorial, 1 factorial. Okay, 2 factorial. Now here, so here we have this 1 is 2, so we have a permute, right? So you have 2, right? 2 states. One is 1, 2, another 2, 1. So you will see here this psi 1, x1, psi 2, x2 plus psi 1 plus 2, x1, y1, x2. And each individual is with sinusoidal function that I will, yeah, to save time, right? So you know this. Okay, so how much degeneracy? Only 1 state, no degeneracy, right? So you see here, that's different. No degeneracy. Right? Because it's indistinguishable, so we only know there are 2 particles, one on the first level, another in the second level. That's all. You cannot distinguish 1, 2, which one in the top, which one in the bottom. Not like this. So for the bosons, the ground state is in this non-degenerate. Then we go to Fermi's. see about the two fermions still without spin, so now still consider ignore spin. Then we are going to step by step, so we're going to take spin. This one also ignore spin first. Okay, so again, the energy will not change. The different only is the symmetry of this wave function, right? Then this, okay. The antisymmetric, since this is a Fermi's, right? So the antisymmetric side A, x1, x2, 3, 1 over n factorial. I'm going to, n is factor 2, right? So that is n1, x1, side n1, x2, side n2, x1, side n2, x2. Since there's no spin, so that is definitely the number of particles is less than the number of states. You have n from 1, 0, 2, 1, 2, 3 until n. So that we will not worry about this later determinant. Okay, so that is general. Now we consider ground state. Again, ground states we go to the n1 and n2, the lowest possible. How about this case? Let's consider if n1 equal to n2 equal to 1. Here, n1, n2 the same. That's 0, right? This later. So, no. Not even this. So we have to go to n1, if n, one of them go to second one. Sorry. Right, only this case. So the occupation here, that is ground state. For Fermi's, that is follow the Pauli exclusion principle. We cannot have the two particles occupy the same states. So that is why for the ground states of Fermi's, the energy is E12, right? Another, so that is 5 h bar squared pi squared over 2 ma. That is the Fermi's. We cannot, and you see the Fermi's ground state is higher than the Boson's. That is due to this Pauli exclusion principle, and that is, later we are going to discuss periodic table. Why the periodic table for each element, they occupy different box or have different behavior, that is because they are fermions. They are the electrons, right? So then follow the Pauli exclusion principle. So okay, now ground states. Antisymmetric, right? Antisymmetric and ground. So now here I just use that formula. The 2 factorial because the number of particles is 2. Then here, psi 1, x1, psi 1, x2, psi 2, x1, x2, x2. Degeneracy? No degeneration. No degeneracy. Okay, just say no degeneracy. Let's look at the first excited states in this case. Again, we have followed the Pauli exclusion principle. If you look at this occupation, still one state have only 1. Then if you go to the next energy lower than this one, so that one of them will go to third, right? So that is occupation. You can see we have 3 states, n equal to 1, n equal to 2, n equal to 3. Now 1, the lowest possible, but the second one, that is the ground state, so have to go to here, right? So that is n1 equal to 1 and n2, so we go to 3. Right? This is how you analyze these excited states of E first excited state is E1 3, which is E1 plus E3, and one is 1, another is 3 squared is 9, so that is totally 10. Right. This is 1 square, this is a 3 square, so that together is, yeah. Sorry?
2ma squared.
Yeah, sorry, yeah, yes. Okay, states. Space finely symmetric was exactly that, we already know this n1 and 2 is 1 is 1, another 3. So we can construct, follow this formula. Psi 1, x1, psi 1, x2, psi 3, x1, psi 3, x2. So this very simple Slater determinant, right? So I just leave here, and you know how to do that. And again, no degenerate, right? Okay, now we go to the challenge one. Is now we consider spin. How to construct spin in this case. Forming this spin up. Okay. So now let's consider. In general, right? So in general, the energy is still same. The total energy is En1 plus En2. The wave functions we totally to be anti-symmetric. Now here, since we have x1, s1, x2, s2, right? Spin and position. So that's, let's use the method which we learned so far. That can be constructed by the spatial. If the spatial is anti-symmetric, then the spin should be symmetric. Or in the spatial function is symmetric, so the spin should be anti-symmetric, right? Let's use this method 1. And then we are going to discuss method 2, how to apply another method. Okay, so we need to construct 4 functions. One for the spatial that we already go to C, we already obtained this this one, right? We didn't use this one. But this for bosons we already have. Then the for spin, so now let's do one by one. Okay. Okay, let's do one by general, then we can go to. So for this one, anti-symmetric in spatial function, we know that is vector, that's a Slater, right? So that is this one. Psi n1 x1, psi n1 x2, psi n2 x1, psi n2 x2. Symmetric n1 factorial, n2 factorial, 2 factorial. Summation P12 psi n1 x1 psi n2 x2. Let's get the general formula, then we go to the details of ground states and force excited states, how to determine those. That is a special, right? So now this spin part, let's get the spin part is same thing. So spin here, it is easy for anti-symmetric vector 2, so the first spin is n s1, s1, comma n s1, s2, and n s2, s1, n s2, s2. Symmetric again we have n1 factorial, n2 factorial, 2 factorial summation p12 and chi m s1 s1 chi m s2 s2. Now we have a general, so now let's go to this symmetric antisymmetric. Now let's consider this. Now this ground state is interesting now. First, it is ground state. Ground states. Let's consider n1 equal to n2 equal to 1 to see if it is possible. We know if you ignore spin, it is impossible, right? But if we have spin, okay. So follow this, right? So follow this total antisymmetric. Now let's construct this and this. Then we can see which one is now. For n1 equal to n1, right? So that energy is simple. Ground. Energy will not change, right? So the E1 plus E1 equal to pi square h1 square or m a square. States. Okay. Okay, so there are two ways, right? So now let us see if we have. So now if we use in the space is antisymmetric. Antisymmetric, I have the index of index. Okay, let's just keep it. And then we go to the details. Okay, we will have a possible two-way, right? Let's consider the first one. First case is antisymmetric in spatial and symmetric in spin. Here, one, x1, x1, x2, x2 is equal to x1, x2, x1, x2. So here, s1, s2, x1, x2. For the ground states, is this formula, right? This antisymmetric, or whatever. Antisymmetric follow this. So that's be 1 over square root 2 factorial. And then here, set 1, because n equal to 1. n1 is 1, n2 is 1, right? So here, set n1 is 1, x1. So n1, n2 is n1, x2. And then say n2 is again n1. Right? If we select n1, n2 equal to 1. So that is antisymmetric in spatial. How much it is? 0, right? Because it's, you see the same row. So no such state, right? So there's no, the first type, ground, equal to psi A, x1, x2. Okay, I'm going to say there's no these states. So now the second case. Second case. Now, this one I construct by the symmetric in spatial and anti-symmetric in the spin, right? x1, s1, x2, ground. S2 is the symmetric in the spatial and anti-symmetric in spin. Okay, symmetric. Let's first get this one. That is this one. So M1 is 2, right? We have 2 and 1. So that is 2 factorial, 0 factorial divided by 2 factorial. And here, you will see that is no permutation because it's all are same. So that's only equal to the product of this single part. Same states, right? M1, M2 equal to 1. That is symmetric. Then spin, if spin and construct anti-symmetric, so that states exist. Still obey the Pauli exclusion principle. So now let's consider spin. Anti-symmetric, in this case, okay, M-1 is plus, let's say, S1, spin up. And another one spin down, right? And this exists, so that is 1 over square root 2. And this is singlet states, right? So if I remember, if I use the Dirac notation, here that is spin. This is S1. In the chapter 7, right, we use this notation S2. Addition 2 angular spin angular momentum M S1. M S2, right? So here S1, S2, M S1, M S2. So the picture is like this. So we have these states, right? So these states, now the finally, now I got. So finally, anti-symmetric ground state is the product is 2, so that is 1, x1, sine 1, x2, and multiply the square root 2, right? Square root 2. And inside, this is singlet state. So that is here. Okay, n I equal to 1. Now we do have 2 states, but one is spin up, another spin down. So that is still obey the Pauli exclusion principle, since when we consider spin, even though the n1 equal to n2 equal to 1, but we still have 2 states, spin up, spin down. So that is not occupy the same state. That is when we consider spin. Okay. If we know the ground states, now let's go to the first excited states. We can see how to construct the first excited states with a spin. Definitely, since this is the lowest, then this must be 1 go to the second one, right? That is so that means M1 equal to 1 and M2 equal to 2, right? So or because this is since indistinguishable, that's it, right? Okay. And in this case, energy. Okay, later maybe this is too much, but I already use this index here, so that's it. Usually ground states I just use state 0, so instead of writing ground, but since I'm there, right here is what I use this. First excited state, right? So that equal to E1 plus E3, E2. Yes. Since we have a spin up and down, so we can multiply that. And that is 5 h bar squared pi squared over 2ma squared. Energy, okay. Now states. States, first excited states. Again, we can have this product here. Right, so now we are going to construct each individual one. So now let's first write down here. Yeah, x1, x2. Okay, let's first consider anti-symmetric. By definition, it's just later psi1, x1, psi1, x2, psi2, x1, psi2, x2. So that is just simply sum over x1, psi2, x2, minus psi1, x2, psi2, x1. That is okay, since this is two different energies, so we can construct anti-symmetric. Then for this case, symmetric, case 1. Case 1, this case 1, I will refer about this case 1, case 2. So case 1, then now let's see how much symmetric. Okay. Then if still first write down this general, and then we are going to play. Here, this n is only for special, right? No restrict on spin. You understand? This is for ms1, ms2 is spin. We have either up and down, this combination of this. But here, this one is index for here. That makes sense? So when this fixed, this one fixed. Did I have a general? This was Ni1, Ni2, right? Or Ni1, Ni1, Ni2, and so that is good. But here, now, ms1 or ms2, we have two values, right? Plus minus 2. So then here we can have a construct several spin symmetric, right? So for ms1 equal to ms2 equal to half positive. It is possible, right? Here. Then we have, I'm going to use 1. And to distinguish how many symmetric, right? S1, S2 is, now how many N1? They are same, right? So here N1 corresponds how many MS1, so that is factor 2, 0 factorial, factor 2, and here this is, since the P1, 2 is the same, right? So that is a half, same, so there's no permutation. Since this between the same states, we will have no permutation. The permutation only for different MSI, yeah, MS1, MS2. So that is, maybe I use this one. So this is S1, MS1, S2, MS2, right? But simply the product is spin up, so correspond to this state. That is possible since the spin, whatever this one, but we consider only construct spin with a symmetry. Now, second one for MS1 is plus ms2 is minus, or, right, or ms1 is minus, ms2 is plus. Then we have another one. I'm going to second, symmetric, s1, s2. So that is 1 factorial, since each one only have 1, right? So this m1 is, and then factor 2. Then here, p, because it is 1, 2, right? So kappa plus s1, kappa minus s2. Then you have a, one is a no permutation, another is a with exchange. So that is finally is, this is also one of these triplet states, if you remember, which one I use. Okay, I use here, so that is. So that is first the kappa s1 minus half s2 plus minus half s1 half s2. Okay, and now let's come down. I use the Dirac notation here, so that is, you know, that is this half, half, half minus half plus half, half minus half, half. And these states, here the states is correspond to I think I mean this one, because you have two states, right? N1, N equal to 1, N equal to 2, so they are all same states. We have one more. Another is 2r down, right? 2r spin down. So then the third one is for m s1 equal to minus half equal to m s2. Both are spin down. Then in this case, we can construct third symmetric spin function, which is now 0 factorial since no spin down, spin up, and 2 factorial, and here 1, 2, and there's no, so this is all negative. So in that case, the only this product of the single spin. That is half spin down. Another is also spin down. So that corresponds to 2 spin down. Okay, how many states here? We have this case one, right? So this one multiplies 3, so we have totally, let's see, I think 3, right? Yes. Totally 3, right? This one totally 3. Now, this is for case 1. We can have 3, and the case 2, now we consider case 2. Case 2 here is we are going to construct the symmetric for this special function and antisymmetric. So symmetric. Okay. Symmetric here, x1, x2 is n1 factorial, n2 factorial, n factorial, summation for all the permutation between 1 and 2, set n1, x1, set n2, x2. Now here we have n1 is 1, n2 is 2, or n1 is 2, and n2 is 1, right? So because this, then you will see here we have a permute. So here, 1 factorial, right? Only one particle in the one state. 2 factorial. And here we have 2 states. One is 1, 2 plus and 2x1 and psi 1 x2. So we have only one symmetric function in the spatial for this configuration that n1, n2 equal to 1 is 1 and 2. So we have only one. Then now how many anti-symmetric for spin? By definition, we know that with 2 factorial oscillator, right? So that is S1, S2, and minus half S1. So that is minus only one, right? So now this is a singular state. If I write down in terms of oscillator, okay, so you can see case 2 we can only construct one state, which is symmetric in spatial and antisymmetric in the spin. This is a singular state, right? So that is a singular state. And then we have these three. Okay. And it's a summary, right? Let me summarize. We have a totally 4 states. So we have a 3, or the triplet state, right? Triplet means 3, right? 3 states. And 1 single state. So the degeneracy is 4, right? How many states? So now let's summarize. So the triplet states here we have 1, that is 1, 2, 3, and then the singular states here is also another one. But these states is correspond to symmetric. I mean, it's in the spatial is antisymmetric, but spin symmetric is plus. Is this one, right? Is this one, this case. Another singular state is spin is antisymmetric, but the spatial is symmetric. Spin and symmetric, spatial symmetric. That is here. So totally we have 4 for excessive states. Okay, so I think I want to go to the next one for the method. Second method to deal with this case, and you will learn it. This is fortunately we have 2 spin states and 2 particles, 2 spins, so we can use this as later determinant. But if not satisfy this, we're going to apply the general. So now we can consider method 2. Method 2 is. You mean method 1 is we construct a total wave function in spatial and total wave function in spin, so multiply. But method 2 is we consider each individual particle has product of spatial and spin, then construct all by antisymmetry. So here method 2 is, when we discussed 1 to 2 is only for the antisymmetry. For symmetry there's no restriction, right? So you don't need worry. For antisymmetry we need to consider. Here, let's still consider this case, right? 2 examples, and then we go to the example with 2 Fermis. with spin half. So in this case, now we are going to construct antisymmetry, right? So now the index is at psi 1, psi 2. Instead of x, the spatial index and the spin, since we combine together, and this means, okay, two particles, right? So antisymmetric, the first one, N1, I'm going to say psi 1. N1, psi 2, psi N2, psi 1, psi N2, psi 2. Here, anyone Ni psi I is a spatial function. In this case, let me consider x, right? Ni, and multiply spin xi mxi. So psi I include the spatial index and spin. So now you can see the difference. Here we first construct a single particle with a product of spatial and spin. And then we construct antisymmetric according to this later. So let's do, you will see you find the same thing, but we are going to use this method. Okay. Now here, for this case, so now here, we in this still follow the example in this D, right? So that is half. Okay, I'll use SI. So this one is SI, right? So here, did I give you? Yeah. So for this one, MSI is plus minus half. In this case, right, 2s plus 1. S is half, so there's only two values. Now for this, then you can construct. Okay, so any antisymmetric function, right? In this case, two particles, two identical permeates. So here, this product is Ni, Ni x1 and psi msi s1. That is this first and second one. Ni x2 psi msi s2. Be careful here. Row, as I said, should be same. That is states, and then the column is number of position, right? So second one is Ni. Okay, N1, let's use N1 to this thing. So that is S1, 1, and N2, since here it is X1. You see the difference is only the states, but the particle position is the same. And then MS2. We do not know they are same or not. S1, S2, we have two values, right? S1, psi N2, S2. Okay, let's MS2, S2. That is general. Already the time. Okay. Let's stop here. I think that I will occupy a little bit more time. We'll keep continuing on next Wednesday. Okay. We need to do the details, and you know how to play. Without do access, it looks simple, but when you do the details, right, you need to know how to deal with. That help you to the midterm last one, right? Yeah, before the midterm, I do not have time to discuss the details, so just give you designs. You do that. So that you had it. So now I think you can work on this, right? Good. Sorry, but I thought that I already give you how to construct spin, sorry, and this mention, the only difference spin or not spin. But, well, okay. All right, that's why I can give you time. So you want to also, you okay, or you want to hindsight? You want to go back? You're fine, okay. All right.
Can I write my name on?
Yes.
Yes.